Right, so complete the description of the device shown by drawing a ring around the correct box. So the device is being used as a electric motor. Remember, when we put current through the wire, this will generate a magnetic field here which interacts with the permanent field, and that causes the coil to spin around. So it is the induced magnetic field inside this coil that interacts with the magnetic field that's already there, and that causes it to start spinning. The coil needs a flick to get started, then one side of the coil is pushed by the force and the other side is pulled so the coil spins. Suggest two changes to the device, each one of which would make the coil spin faster. So we could increase voltage, or we could increase the strength of the magnetic field. Suggest two changes to the device which would make the coil spin in the opposite direction. Well, we know if this is a positive and negative, then we can change the battery around. So we are swapping the polarity. Swapping polarity. So that's, we've got plus here and minus there. We're swapping those two around, and that will change the direction of the current. The other thing we can do is, if we've got a north and a south pole here, if we swap the north and south pole around, then we'll get it to spin in the opposite direction. So swap poles of magnets. Right, so when a conductor carrying electric current is placed in a magnetic field, a force may act on it. So you can see the direction of the force is up. But we need to make sure we know how to do this. So if we go from north to south like this, the field is cutting. We've got a current which always goes from the positive, which is the big one, so the current is going that way. And if we used our left-hand rule, we could work out the reason the force is going up, and that is because the field goes this way, the current is coming towards us, and therefore the motion is up. So first finger is for field, second finger has got a C in there somewhere for current, and our thumb has got an M in there for the motion. So remember, these are all perpendicular to each other, and that will tell you the direction. This is Fleming's left-hand rule. Right, state two ways in which this force can be increased. Well, we just talked about those. We could increase the voltage. We could have more turns on a coil, but in this particular instance, we can't really change the conductor because it's just a piece of wire, so we could have a increased magnetic field. So we have stronger magnet. To spin in the opposite direction we've discussed, so this is the same question. In what circumstance will no force act on a conductor carrying electric current in a magnetic field? So if we have a conductor, if the magnetic field is going from north to south and the conductor lays parallel to the field and the current goes in the direction of this, then you will have no effect. So remember, when we've got a field like so, the conductor has to be perpendicular to the field. So the current goes this way and the field is going this way. If the current is going parallel to the magnetic field, so this is our current in a wire and this is our magnetic field, there will be no motion, there will be no force created. So when conductor is parallel to the field. Right, this question's irrelevant. I'm not sure why it's on there, so it's not really relevant. The next question, the diagram shows apparatus used to demonstrate the motor effect. Remember, the motor effect is when you get a force. So when the wire moves, it's called a motor effect. X is the short length of bare copper wire resting on two wires. So you've got a red and a black, and it says this is the negative, so we know that this is the positive, therefore the current is moving along here and down there. So we know going through here the current is coming towards us. So current. The field is going straight down. So I'm going to draw this current again slightly like this, so it's easier to understand that the field is going from north to south like that. So if our first finger points down with the field and our second finger is the current, then we know that the thumb is going to point in this direction. So we're going to get motion to the right. Right, describe what happens to the wire when the current is switched on. So the first thing is the wire feels a force, and the reason it feels a force is because the current induces a magnetic field which interacts with the permanent field. Now I'm not sure this part is essential in the question, but it's really important that you write this down on a 3-mark question. So the reason things move is because when you create a current, remember, in a wire, a magnetic field goes around the wire, and that magnetic field that you've created with the electromagnet interacts with the permanent field. So this is a south and this is a north. It interacts with the field that's already there, and this creates a force. So by putting a magnetic field into a field that already exists, you're going to get some force on the conductor. So wire feels a force, and that's because the magnetic field that you've induced interacts with the permanent field, and that forces wire to move right, as we've discussed up, and it will move right horizontally. So this wire is going to go in that direction. What difference would you notice if the following changes are made? Well, if we change the magnetic field, we would have the opposite. So we would know that the current is still coming towards us. This time, our field is going up, and if we used our left-hand rule, we know that the direction would be to the left. Now you know this because flipping it, as we described in other questions, is always going to create movement in the opposite direction. However, it's really important that you practice. So if you're not certain how to use your left hand to do this, then practice on these diagrams and make sure for your real exam you are able to see which direction it will move. Right, if we increase the current, it will feel a greater force. Now while we're on this, remember, if we have force is equal to mass times acceleration, the mass of the wire is the same. If we increase the force and they are proportional, you know that you are going to get a greater acceleration. So it feels a greater force, so accelerates faster. Right, the diagram shows a coil placed between the poles of a magnet, and the arrows on the sides of the coil itself show the direction of the conventional current. So this is one of those tough questions, because in this particular question it's not going to rotate. Why is it not going to rotate? Because there is no split ring commutator. Remember, normally you have a split ring that looks like this, and then that part is connected to the coil. Sorry, that should be in like that. And when this is connected to the positive and this is connected to the negative, it causes it to spin. Then when it gets to the half turn here, there is no connection with the positive and there is no connection with the negative, so the current comes off, and then as it spins round again, this part is reconnected with the positive and negative, and this causes it to spin 360 degrees. So you will only get this with a split ring commutator. Here we have no split ring commutator. So what's going to happen when it starts to spin? The positive terminal which is positive here and negative here. So this is creating, this is on the positive side, this is on the negative side. So it's going to move down here, and then this side's going to be going to be on the negative. So this side's going to move around to there. But as soon as it gets to there, because it's still negative, on the other side it's just going to flip back. And all that's going to happen is it's going to continue to flip. So it's going to go flip to there, then it will flip back, and then it will flip, and then it will flip back. And this is going to keep happening until eventually it remains kind of in the center. Now if you imagine it was in the center, then because it just flipped and flipped and flipped and flipped and eventually it stops, it's just going to kind of oscillate and vibrate something like that in the center, and the actual coil is going to look vertical like so, rather than this horizontal one. So this will be vertically propelled. So how do we describe this? The coil spins 180 degrees. When this side gets to the other side, it then wants to flip back, then spins back. Eventually it's going to keep doing this, and the reason it's doing this, due to having no split ring commutator. So the reason it's flipping forwards and backwards is because there's no split ring commutator, as we described before. And you can use my videos to look at this in more detail, because I've explained it using an animation, which really helps. So the coil spins at 180 degrees, then it spins back due to having no split ring commutator, and eventually, as we described up here, it would align or oscillate in the vertical position. Right, most electric motors use electromagnets instead of permanent magnets. State 3 features of an electromagnet which control the strength of the magnetic field. Well, if we look at this, we can look at the number of turns, so number of turns, and that's on the coil. Remember, we don't say there are more coils, we say there are more turns on the coil. So that's the number of times the wire is wrapped around the coil. The next one is the current. So we can control the current, and we know that if we increase the current, we will increase the strength of the magnetic field. The next one I just want to talk about is if we look at F equals B times I times L, then to increase the force, which is really what we're talking about here, we can increase B, we can increase I, and we can increase L. So if we talk about this, well, this is the length, this is the magnetic field, and this is the current. So 3 features of an electromagnet which control the strength of the field. Well, this is the magnetic flux, and that is basically down to the strength of the electromagnet. Now it's controlling the strength of the magnetic field, so what we can't really do is change the magnetic field of a permanent magnet. So we can't really do much about this because it's a permanent magnet, so there's not a lot we can do. If we change the current, we change the magnetic field around the induced magnet. So we can change the current, we've talked about that here. And the other thing is the length. Now the length inside, so if this is our coil and we have lots of turns, which we've described, we are increasing the area of the conductor inside. So this could also be the area of conductor inside the field. So how do we do that? Well, if you look at this, if we have one wire going through the magnetic field and we compare that to having lots of turns, and we have in the field, if we've got 1, 2, 3, 4 wires, we're going to have 4 times the magnetic field generated. So therefore, having a greater area of the wire, the conductor in the field, is going to create a much bigger electromagnet. Right, many electrical appliances use the circular motion by their electric motor. So we know a drill basically, does it spin? Well, yes it does. Does a fan spin? Yes it does. Does a mixer spin? Yes it does. Does an iron spin? No. Does a kettle spin? No. These both have elements that just get hot. Does a screwdriver spin? Yes. Right, one simple design of electric motor is shown in the diagram. It has a coil which spins between the ends of a magnet. Give two ways of reversing the direction of the force on the coil in the electric motor. Well, the first thing I'm going to do is I'm going to work out the direction because it's really helpful. Can you see here it's got a split ring commutator? So this is going to enable it to spin 360 degrees because it's got this hole down the center. So make sure you understand how that works. Right, it says here it's going to rotate clockwise. So the force here is going up. Well, how can we work that out? Well, we know we've got a north pole and a south pole. It's going to go from north to south, like so. We've got a coil inside this field, like this. And we know we've got a positive there and a negative on this side. So we know the current's going to go from the positive to the negative. So it's going to come down this way. So if we look at the south side, we know that the current is going into the page. Remember, when we're doing this, our second finger represents the current, and our first finger is the field, which is going this way. And if you position your hands, you should get motion going down. So we've got current. This is not going up, it's going into the page. As you can see, it's going that way into the page. Here we've got the field, and it is going in that direction. And this shows that this is going down. So current into page. The field is going down. Sorry, the field is going from left to right. And the motion, which is generally called the force in exams, is going down. Now, the opposite would be on the other side. So with the current coming towards us, field still going in the same direction, we will get motion going up. So we know that this side spins up and this side spins down. Now this question isn't really about that, but I just wanted to make sure that you are able to answer that question and you are able to decide the motion based on the current. And you also need to know that the big line on a battery represents the positive and the small represents the negative. Right, how can we reverse the direction? We could reverse the direction of the battery, so change battery around. I've said earlier we are changing the polarity, or we are changing the terminals, so we're going from positive to positive. What else could we do? Well, if we've got a north pole here and a south pole here, we could swap those two around. So we could change the poles on magnets. Give two ways of increasing the force. Well, again, we've talked about this a lot. We could have a stronger magnet, which would increase the magnetic field. We could have a battery with a higher voltage. We could have more turns on this wire. Lots of different things. If we had a greater area of the coil cutting through the field lines, then that would also give a greater force. So any of those things is going to increase the size of the force that's acting on the coil. Right, a science technician sets up an experiment shown below to demonstrate the motor effect. Right, the copper roller is placed across the metal rails. When the switch is closed, the copper roller moves to the right. So we've got a positive here and a negative here. So we know it goes from positive to negative. So it's going to move this way. So the current is moving that way around the wire. The field is going from north to south. So if the field goes from north to south, and we know that the current is coming towards us, so we need to use our left-hand rule. If the current comes towards us and the field, the first finger is our field going from north to south, then we would know that the direction is going to move this way. Right, complete the sentence by drawing a ring around the correct line in the box. The copper roller is placed across the metal rails. When the switch is closed, the copper roller moves to the right, as we've just described. This happens because the copper is an electrical conductor. Now, I know again it's told you the direction, but you need to be able to do this, so make sure you practice. Suggest one change that the technician can make which will cause the copper roller to move faster. Again, we can increase the current. Suggest two changes which the technician can make, each of which will separately cause the copper roller to move to the left. Again, we're going to swap the poles, or we're going to swap the terminals. So therefore the power supply, we would say, is we're going to swap the current. We're going to swap the direction of the current by changing the connections on the power supply. We're going to make that a negative, we're going to make that a positive. So be specific about what you're going to do with the power supply. Right, the next question says, generating more electricity to power the increasing number of electrical appliances raises an environmental issue. The number of electrical appliances used in the world's richest countries is increasing, yet many people in the world's poorest countries have no access to electricity. What type of issue does this inequality between people in different countries raise? Well, that is an ethical issue, so about poverty.